and how they are associated with all the statistical probability distributions, because oftentimes what happens is you might be given two different distributions following a data set following two different distributions, and you might be asked to find some values which are in accordance with a rule. Let's say x and y are two data sets, are from two different data sets, and you might be asked to find the distribution of x plus y or xy or x divided by y and stuff like that. So in that case we would require the joint distribution. So the process to find that and how to manipulate and how to use them is what we are gonna study in this whole lesson. So let me just prepare the session and then I'll write down the topic. Okay, so joint distributions. Now we are going to study a lot of things here. So firstly, let us start with this exact thing. Two random variables So what we are going to say here is two random variables x and y are said to be jointly distributed with the joint PDF fxy x comma y such that double integration over the region A f xy x comma y dx dy. So like this is how we are going to solve these problems. Now this is how the joint PDF would be defined. Now this region which we are talking about, this A is a two-dimensional region obviously, and we need to be careful about the region of integration in this kind of problems, because well what we know from this is if omega is the sample space where then what happens is we have, by the, since total probability is always 1, then equals to 1. So this is because the total probability is 1. So this is how we are basically trying to shape things. Now this kind of problems might be tricky at first sight, so that is why we would be doing a few examples to make sure that we understand all the problems and all the key features of joint distributions. So let us start with our first example of whatever we have studied till now. So let me first write down the entire problem and then we can discuss. Not y, actually it should be 1. So this is the question. So I will just state the whole question and explain it to you first, and then I'll give you like a minute or so to try and figure out the method of approach, or how we are going to actually attack all these three different problems associated with this statement. So it's given that x and y are two jointly continuous random variables. So it means that x and y are random variables and they are jointly continuous. So they are associated with each other and they have a common PDF. So that joint PDF is basically f of x comma y, which is a multivariate function. And when x and y both lie in the range 0 to 1 inclusive, we have the PDF as x plus cy square, where c is some real number and it is 0 otherwise. So what we do understand is it is only possible inside the range where we have 0 comma 1, right? So one thing is clear. One thing is clear, that if you have this graph here, so inside this rectangular region, the joint PDF fxy is defined as x plus cy square, and otherwise in outside of all the regions, outside of this region, in everywhere it is 0. So that's basically what the problem says. Anyways, so this is the statement, and then we have three problems. We have to find the constant c, we have to find the probability that 0 less than equals to x less than equals to half, and 0 less than equals to y less than equals to half. And also we have to find the expected value of x into y. So I'll give you like 1 or 2 minutes, probably 2 minutes, to try and think a solution to the first part, and then I'll solve it. Okay, so I think this is enough time to make sure that you have found a solution. So even if you have not, nothing to worry about, because we're going to learn it, and once you learn it, I do not think there would be any problem in solving any kind of problems like this from now on. So well, first let me write down the PDF again. It is x plus cy square only when x comma y belongs to 0 comma 1 squared, right? Now we see that in order to find this this constant c, we can use a condition that total probability is always 1. And how do we use that? So see, so since total probability is always 1, we understand that the integration over the region 0 comma 1 to 0 comma 1, that is the rectangular region of the joint PDF, would result in a 1. Now how do we do that? Well, it means that 0 to 1 and 0 to 1, because x and y are independent of each other right now, so we can write it directly as x plus cy square dx dy equals to 1. Now, so the inner integration turns like this. It's with respect to the variable x. So obviously integration of x is from 0 to 1 is 1 by 2, and for cy square it just remains as cy square dy equals to 1. And then again we have 0 to 1 half dy plus c times 0 to 1 y square dy equals to 1. Now this gives us 1 by 2 plus c, and this is y cube by 3 from 0 to 1, right? Because the integration for y square is basically y cube by 3. Now 1 by 2 plus c by 3 is equals to 1. This gives me c by 3 equals to 1 minus 1 by 2 equals to 1 by 2, and therefore from this equation we get the value of c is 3 by 2. So this completes our first part. Now let's go to the second part. We are required to find this of 0 less than equals to capital X less than equals to 1 by 2, comma 0 less than equals to capital Y less than equals to 1 by 2. And since we already know the joint PDF, it's easier for us to find this, because this only equals 0 to 1 by 2, 0 to 1 by 2, the joint PDF, which is basically x plus 3 by 2 y squared dx dy. And from this we get the outer integral remains intact while the inner integral evaluates like this: x square by 2 plus 3 by 2 y square from x equals to 0 to x equals to 1 by 2. Okay, and dx dy. So the plus 3 by 2 y square just remains same, and this one is basically I of x. So anyways, this becomes 0 to half. For the x square by 2 part, it becomes 1 by basically 2 cube minus 0, and this one becomes 3 by 2 y squared into 1 by 2 dy. So the x part is completed. Now this means it's 0 to 1 by 2, 1 by 8 plus 3 by 4 y squared dy. Therefore it becomes 0 to 1 by 2, 1 by 8 dy plus 0 to 1 by 2, 3 by 4 y squared dy. Now 0 to 1 by 2, 1 by 8 dy is simply 1 by 16, and this one is 3 by 4 comes outside, and integration of y square is y cube by 3, and it is from 0 to 1 by 2. So let us do this one. 1 by 16 plus 3 by 4 multiplied by, now this becomes 1 by 3 into 8, and the 3 is cut off, so it becomes 1 by 16 plus 1 by 32. On simplifying, you see that this is 3 by 32, which is the answer for the question. So we have solved it successfully, and now it's time for finding part C. E of xy is given as, now we are going to use the limits over all the integrals, over all the region basically, because we would need it to be 0 to 1, 0 to 1, xy, fxy, x comma y, dx dy. Now this is going to be a long integral because let's see, 0 to 1, 0 to 1 xy times x plus 3 by 2 y square dx dy. We can separate it into two integrals as follows: 0 to 1, 0 to 1 x square y dx dy plus 0 to 1, 0 to 1 x y cube into 3 by 2 dx dy. Now you see this x and y here are independent and they can be multiplied together, so we can evaluate the integrals of x and y separately and multiply them together, right? So this becomes 0 to 1 x square dx multiplied by 0 to 1 y dy plus 3 by 2 0 to 1 x dx multiplied by 0 to 1 y cube dy. Therefore 0 to 1 x square dx is simply 1 by 3. Okay, let me just write it correctly. 1 by 3 multiplied by 1 by 2, and this one would be 3 by 2 multiplied by 1 by 2 multiplied by 1 by 4. So it becomes 1 by 6 plus 3 by 16, and they have a common LCM of 48, so it's basically 8 plus 9, which is 17 by 48, which is the answer, and thus this is the joint expectation of the variables. And you see that this kind of integrations require a lot of different kind of techniques and stuffs. So anyways, the video for integration would also be embedded at the end, and you can watch that, so that you do not have any doubts regarding integration, because I do that in every video, and same for this video, it's also attached at the end. The null hypothesis is written as h naught, which is this, while the alternate hypothesis is written as h1. Okay, and what we can do is we can understand this from various examples, and we can understand that this kind of problems have a lot of ways to be acceptance, but obviously first we are trying to understand how to handle this. So a null hypothesis is something which is given, and we would like to say some parts about it, some parts about the null hypothesis, where how we can handle, like let's say if the null hypothesis is theta greater than equal to 2, then the alternate hypothesis should be theta less than 2. So what happens is, if h naught belongs to the set A and h1 belongs to the set B, and if U is the universal set, then we must have A union B equals to U, while A intersection B equals to phi. This is what it should have, because the null and alternate hypotheses are basically reverses of each other, so they are complementary. Now, that being said, what we can now do is we can understand it from an example, and while also understand the various terms involved, like type 1 error, that we reject h naught when h naught is true. So type 1 error is defined as when we define type 1 error as the event that we reject h naught when h naught is true, and we can find the probability of type 1 error, right? So it basically is this. Now, one more thing is level of significance or significance level, which is usually denoted by alpha. So we set a significance levels beforehand for our test, and we say that if okay. So well, obviously this is what we call as the type 1 error. So probability of type 1 error given theta if it is less than equals to alpha, which is significance level, and this usually gives us that the test is significant and we should proceed with it. But if the probability is greater than that, then there are other ways to test that. Similarly, there is a type 2 error. So this is called type 2 error, and it means that we are going to accept h naught when in reality h naught is not true, which is h naught is false. So this is also a type of error, and it is called basically type 2 error, where or we can also call it bit of theta. So there are various ways of doing that. So since it is usually denoted by beta, you can write beta of theta, where theta is the parameter of the test statistic. Now, so we are given this entire thing, and now we are going to understand each and every problem in a very similar way. So what we are going to do is we are going to do 3 more examples, and very typical and very nice examples actually. And what happens is, when we do these examples, we are going to need a lot of basic theory, and theory that we have studied in statistics and theory that we have just studied right now, which is basically the application of these things. So I'll give you a minute to understand this on your own, and then we can start. Now for the examples part, I'll write down the questions first and then we can solve them. So consider a radar system that uses radio waves to detect aircraft. The system receives a signal and so understand the problem carefully first. Read it once again when I complete finishing it. When I finish the problem, and then after a while we can start discussing the solutions one by one because there are multiple parts to this problem as well. So up to this part we are clear because what we have said is this, and we understand what W is. W is basically a standard normal variable, a normal variable, a normal random variable with mean 0 and variance 1 by 9. Now, That brings question A. So I'll explain the problem again, but let me just write down the questions. There are 5 such questions. So the first one is write the null hypothesis. Write the null hypothesis and the alternate hypothesis in the terms of theta. So that completes the questions, and now let me explain how do we actually do it. So basically, it says that consider a radar system that uses radio waves to detect aircrafts. So there is a radar system that uses the radio waves and it detects aircrafts are present or not. So this how it works is the system first receives a signal, and based on the received signal, it needs to decide whether there is an aircraft present or not. Right now, if X is the received signal, and we already know that if X is W, then there is no aircraft present, and if X is 1 plus W, then there is an aircraft present. Right now, here W is just W belongs is basically a normal random variable with mean 0 and variance 1 upon 9. So that's the probability distribution of W. So W takes values according to which has probabilities according to a normal distribution with mean 0 and value variance 1 by 9. Thus, what we can do is we can write x equals to theta plus W. We're just trying to introduce a parameter, and you would notice that if theta is 0, then x is basically W, which means there is no aircraft present, and if theta is 1, it means there is an aircraft present, and we can write x is 1 and 1 plus W. Now suppose that we define the null hypothesis H naught as no aircraft is present, while the alternative hypothesis H1 as an aircraft is present. Now the questions. Let's go for number 1. Write the null hypothesis and the alternative hypothesis in terms of theta, right? So the simple hypotheses are as follows. Part A, we have that H naught, which is the null hypothesis, it can be written as theta equals to 0. That is no aircraft is present. Then we have H1. H1 is basically the alternative hypothesis. So let me write down alternative, and this is theta equals to 1. That is aircraft is present. Okay. Now to decide between H0 and H1, we look at the observed data, obviously, and this observed data tells us if we can differentiate between H0 and H1. That completes part 1. Let's now for B, design a level 0.05 test to decide between H0 and H1. So when we say a 0.05 test, what we actually mean is we are trying to decide, we're trying to make a test which can help us distinguish if to decide between what is true, H0 or H1, what to accept and what to reject, and the level of significance should be 0.05, which should be our helping hand. So to decide between H1 and H0 and H1, we look at the observed data. The observed data is just the random variable x, right? The observed data random variable x under H0 x follows normal distribution with mean 0 and variance 1 by 9, and under H1 what happens? So this is under H0, right? And under H1 what happens is it follows normal distribution with mean 1 and variance 1 by 9. Why is it so? I'll explain that. Because under H0 W, therefore E of x is equals to E of W, and W is a standard normal variable with mean 0. So this is this, and also variance of x should just be variance of W, which is 1 by 9. Therefore x also follows a normal distribution with mean 0 and variance 1 by n. And under H1 x is 1 plus W, and this means E of x is simply so the mean is 1, and adding a constant to the variable doesn't change its variance, because variance of x then would be variance of 1 plus w. Therefore x follows normal distribution with mean 1 and variance 1 by 9. So yeah, that's how it works. Now the test. Now what we are saying here is we can suggest the following test where we choose a threshold c, and if the observed value of x is less than c, we can choose h0. Otherwise, if it is larger than c, we can choose h1. So that's what we are going to do. Now to choose that c, we are going to use our required alpha. So let's see. Probability of try 100 is basically reject h0. Was we made sure that the probability portion got into multiple random variables and stuff like that. Now our entire goal of this was to study higher probability and statistics, which we shall begin, and for that we need to know the basic to intermediate portions of statistics and how all those probabilistic criteria and solutions would actually work in a real life scenario, right? So I'll just write it down and let us see. So what we are doing is we are beginning a bit of statistics here. So in statistics we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2 and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is We can find the mean, the mode, the median. We can find the skewness, the kurtosis. Also, we can see if they fit into any probability distribution. And moreover, what we can do is we can find probabilities of certain heights being improbable, or certain heights being like very likely, right? And maybe there are more than 10 people, maybe there are like 1000 people, and we did a random sampling of those 1000 people, and we selected 10 people at random, and then we selected the heights. And from this heights, what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1000 people. Can we get an idea about the height of the population from the from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example. And what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years, but that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased. Every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like, what is the average height of the population? Ideas like, what is the height that goes on the furthest? Above which range do we have a 20% chance of getting a certain height, and stuff like that, So we shall begin with something called mean. So what is the mean? Let me write it down. Right. Similarly, the median. So if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now, since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it were not even, let us say we had 5 quantities, then there is only one middle number, that is the third one. So we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So an example of a statistics would be so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of an estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see, so that is how bias is defined, and we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore we see that e of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and our problem is solved. Now this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now after this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap, because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta, so it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is So the MSE is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that, and we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean E of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then EXI is simply fx dx, while variance of xi is x minus EXI squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square, and now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1 by n square variance of summation from I equals to 1 to n xi, and this would be n into sigma square, so it becomes sigma square by n, right? Therefore probability that theta n cap minus theta is greater than equal to epsilon is less than equals to sigma square by n epsilon squared. Therefore limit n tends to infinity, probability that theta n cap minus theta is greater than equal to epsilon is less than equals to 0, and this means that obviously since probability can always be is always greater than equal to 0 as well, therefore limit zero. So theta n is an estimator of theta, and this is proved. And added with this would be also the required videos for integration as well, because we needed it here and we would need it in other videos as well where it would be embedded as well, so you can just watch that if you want to see some parts of it, or you can skip that. The next video we shall again go on to do some other consistent estimator things. Given that h naught is true, or given that h naught, right? This means when we reject h naught is x greater than c, right? And when h naught is true, it's basically h naught. And this means that x greater than c given h naught, under h naught, so when h naught is given, it means that x follows a normal distribution with mean 0 and variance 1 by 9, right? So it only means that this is w by c, and this can be written as 1 minus phi c, where phi is the standard normal CDF. Right? Actually, not phi, it's 3c, because I'll explain why. it should be like this. W has a variance of that, so we have to divide both sides by the standard deviation, which is this, and only then W by 1 by 3 is a standard normal variable, and then we can write probability of Z greater than 3C. This is equals to 1 minus phi of 3C, right? Now the type 1 errors probability is usually the significance level, then alpha equals to right. This means therefore C is basically 1 upon 3 phi inverse 1 minus alpha. Now when we let alpha equals to 0.05, since alpha equals to 0.05, we have C equals to 1 by 3 phi inverse of 1 minus 0.05, and if you calculate this, what you get usually after dividing by 3 is 0.548, which is